Sawadee ka. My name is Jenny Soonthornrangsan. I am a PhD candidate at TU Delft, and thank you for the introduction. Like the introduction said, I will be discussing preliminary hydrological data analysis for the Bangkok area. So I know that FEMCA has introduced the project to also include a sea level analysis, but since the project just kicked off, I'll be focusing primarily on the first stage, which involves groundwater and subsidence. So earlier studies have shown a strong correlation between substantial pumping in the Bangkok area as well as significant subsidence that occurs throughout the city. And so in response to those studies, the government introduced measures to start regulating pumping. And they've started that since the early 2000s. And now we see that groundwater has recovered mainly to where they were before the pumping. However, what we see today is that subsidence continues to occur at lower rates. And so our goal right now is to investigate the historical and the current relationship between groundwater and subsidence to ultimately be able to simulate subsidence based on various pumping scenarios for the future. And we're also interested in doing this at various locations throughout the city. And so I would like to introduce a method that Femke had mentioned called time series analysis. And this particular method is really powerful in that it's able to allow you to see the individual effects on a time series that you're interested in. So for example, for groundwater, you can look at the individual effects of, say, pumping and groundwater diversions or climate change, such as changes in precipitation and evapotranspiration, and seeing what those effects are on groundwater levels and seeing which ones are the important ones. And so I would like to demonstrate by showing you an example. And so this first upper graph here is a time series of measured head. And so you see the daily variations increasing and decreasing. And this particular well is located near the ocean. And so some of the inputs that they are interested in is the sea level. And so here the sea level mimics groundwater levels quite well with the daily variations. In this green graph here, you have a time series of rain. And then in this bottom graph here, you have a time series of the discharge or the pumping. And so based on these three inputs, sea level, rain, and discharge, you can simulate groundwater levels to coincide pretty accurately with the time series of groundwater levels that you observe. And so here simulation is shown in blue, whereas observed is shown as the black dots. And so you see that it's mimicking that daily fluctuation quite well. What's also neat about this technique is that you can see which of these inputs have the most significant contribution to our simulation in head. And so as you might have guessed earlier, seeing that daily variation in sea level might allow you to deduce that, that was the input that was going to have the most influence on head. And so we would like to be able to utilize this technique on our project as well. And so with time series analysis, we want to answer the following questions. How much is pumping actually contributing to the groundwater head variations that we see? And then subsequently, how much is pumping contributing to the subsidence variation in Bangkok? And so with this time series analysis for this project, we would like to first start off with developing time series analysis models for groundwater levels. And these are the stresses or the drivers, the inputs that I mentioned earlier that we would like to input into our model. So that would be groundwater pumping, meteorological data, and that would be important in terms of recharge into the aquifer. And then lastly, the river stage, which is mainly important for the wells close to the Chao Phraya River. And then once we have these, we would then develop time series models to simulate subsidence. And now we would have the inputs as the stresses that I mentioned earlier, but now also groundwater levels. And so first off, I just want to cover briefly what we have in terms of data that's going into our model. So here we have the location of well nests located throughout the city, courtesy of the Department of Groundwater Resources. And so here you could see that our well nests are located throughout the city, as well as in Soonthornrangsan, east to Minburi. So it's located quite well, distributed quite spatially well. Each of these well nests have wells that are drilled into different aquifers. And I'll show you an example of that later. So some well nests will have some wells that are drilled into the PD aquifer that Famke showed, or the NL aquifer. Next, not only do we have groundwater data, we also have subsidence data. And so here, shown for the southeastern region of the Bangkok area, I show that the INSAR data that we have from Sentinel-1. And so this is subsidence levels from about 2016 to 2021. And this is relative. And so you could see that relatively, most of this region is not subsiding much anymore, but most of that subsiding areas are concentrated in the southern regions, in the Soonthornrangsan region, as well as the eastern regions shown in red. Not only do we have INSAR data, but we also have leveling benchmarks data, courtesy of multiple departments from the government. And so for our Bangkok groundwater, I would like to show you the groundwater levels for LC-SPK007 here, demonstrated by that blue arrow. And so for this well nest, I am showing head groundwater levels for two of the wells. One well, shown in red, is located in the PD aquifer, and this is the shallower well. And then the other well, NB, is the deeper well. So here you could see that in the mid-1990s, we see a dramatic decrease in head. And then from about 2000 on, we've been seeing it gradually increase and steadying out. And so what is causing this? What is causing this trend? And so one of the things that we think is causing this trend, or having a significant influence on it, is groundwater pumping. And so this bottom graph here is showing the estimated total pumping, shown as this top line here. And it's increasing from the 1950s onwards and maxing out in the mid-1990s. And so that's correlating quite well to this drop in head in groundwater levels that we see in the mid-1990s as well. And so that's one of the main correlations that we see just visually already. Now, we want to include all of this into a time series analysis model that I mentioned earlier. So we're inputting things such as meteorological data, groundwater pumping, a river stage if we have it, and we want to first simulate groundwater, and then we want to simulate subsidence. And so this is just an initial attempt to simulate subsidence that we have. And we want to do this for the historical period when we have a lot of pumping, and then for current periods when the government has introduced measures and there's not a lot of pumping going on. And so this is our first look at simulating subsidence for this well NB30, and our observations from benchmark leveling campaigns are shown in black. And so you see that subsidence back in that region, back in that period, was around 5 millimeters per year, which coincides with what Wim talked about earlier. And so our simulation, based on the inputs that we gave, are shown in blue. And so that's fitting relatively quite well with an R squared of about 80-ish%. Now, we also want to look at simulating subsidence in the current period when there's not a lot of pumping. And so what we see here is that observations, again, are shown in black, and then our simulated is shown in blue. And here we have a lot of noise. So this subsidence observation is from INSAR, and it's showing a lot of noise. And so our simulation is not, the fit is not quite good, but we see that it is capturing that slight negative trend that we still see to this day. So the lower subsiding rates that we see. And so some initial takeaways from starting off this project is that we do see correlation between groundwater pumping and subsidence. This is especially true during the historical periods when we see substantial pumping. However, for current periods, this is harder to interpret, with less pumping going on. And so factors such as meteorological data, influencing recharge may be more important during this time now. And the strength of the correlation, how strong that correlation is also location dependent as well. And a lot of people are also interested in the effect of loading from buildings. And so since we don't have a time series of loading from buildings, this effect is not quite known yet. And so moving forward, we would like to clean up that subsidence time series in the current period and to be able to simulate that much more accurately. And so thank you for your time and your attention.